Hi, so this is the 2017 Stout 110 live solve. This is problem 7. As usual, I recommend you go through this problem first on your own and then return to this video. Um, but if you've already done that, well, yeah, let's get started. So this is a beta kind of problem, Bayes, serum, maybe Bayes billiard stuff. Um, so a new treatment, Bayes serum, has been developed for the disease conditionitis. A clinical trial is about to be conducted to study how effective the treatment is. Bayes serum will be applied to N patients who have conditionitis, and given P, the patient's outcomes are independent, with each patient having probability P of being cured by the treatment. But P is unknown. To quantify our uncertainty about P, we will model P as a random variable with prior distribution P as unit 0, 1. So that's a classic Bayes binomial Bayes conjugacy thing. Um, beta, wait, beta binomial conjugacy, which is like one of my favorite things in this class. Okay, so part A says find the probability that exactly K out of the N patients will be cured by the treatment, unconditionally not given P. Your answer should be fully simplified. Half credit is available for answer left as integral. So integral, that seems promising. So if we do know P, but that's not unconditionally, we have that this is going to be just like a binomial. So it's N, choose K, P to the K, and 1 minus P to the N minus K. But this is for the case that it is like this is just if we know P. So what we're going to do is we're going to integrate over P, and P right now is uniform, so we can just go dP from 0 to 1 since we generally would like lotus that thing. So let's just like, we can take out the N, choose K. So this is going to be equal to N choose K from 0 to 1 of P to the K, 1 minus P, N minus K. You can solve this with Bayes billiards. I think at the time when I took this final, I didn't really know Bayes billiards. And now I don't really have it stuck in my head, but I am able to pattern match like betas. And I see that this looks sort of beta. And it sort of looks like the beta K plus 1, comma, N minus K plus 1 PDF. But the beta, that thing PDF is going to be gamma. It's like gamma A plus B over gamma A, gamma B is the constant in front. So that's gamma N plus 2 over gamma K plus 1, gamma N minus K plus 1 is the constant in front. And so this constant times this, when we integrate it, integrates to 1, which means just this will integrate to the reciprocal of this. So we have that this is equal to N choose K times the reciprocal of this thing. So that's gamma K plus 1, gamma N minus K plus 1, gamma N plus 2. And for integers, we know that we can turn just like we have gamma N equals N minus 1 factorial. So this is equal to N choose, so this is just the binomial coefficient here. And then here we have K factorial times N minus K factorial over N plus 1 factorial. And here everything cancels. So this guy canceled, this guy, and then we're just left with 1 over N plus 1. So this is going to be the unconditional probability that exactly K out of the N patients will be cured, which is pretty cool. It actually doesn't end up depending on K at all. Okay, so that's part A. So now for part B. Now the treatment is extremely effective in the clinical trial. All N patients are cured. So we had a binomial trial of like N patients and all of them were successes. Given this information, find the probability that P exceeds 1/2. And note that P is a random variable. And given the information, we now have like a prior distribution on P. Your answer should be fully simplified and expressed in only in terms of n. So we have p currently as unif. This is our prior distribution. Note that this unifs are equal to beta 1, 1. And when we do the posterior, so p given data is going to be distributed by beta binomial conjugacy to 1 plus the number of successes and 1 plus the number of failures. So we add the failures to the B and then we add the successes to the A. So now we have it is going to be distributed beta n plus 1 comma 1. And we want to find the probability that P exceeds, so is greater than 1/2. And this is going to be like the inverse of it, like, or this is going to be some sort of like CDF-ish thing. So it's going to be 1 minus the CDF. Little p is less than or equal to 1/2. Because it's continuous, I can keep the like equal to. So 1 minus the integral from 0 to 1/2 of the beta, which is gamma A plus B. So n plus 2 over gamma n plus 1 gamma n, or gamma 2. Oops, gamma 1. And this is times p to the like p to the n plus 1 minus 1, so n dp. So this is the beta n plus 1 PDF, which you can just look up on your table of distributions, and we're integrating because it's a CDF. Okay, so we can compute this because n is a integer. So this is going to end up being like, well, we also know that like this divided by this, or this divided by this is going to just end up being n plus 1 from like one of our fun facts about just gammas. So that's pretty useful. We have, yeah, so we have, this is equal to 1 minus integral of, I'm just checking to make sure my constants are all good. Yeah. N plus 1, p to the n, dp from 0 to 1/2. You can take the n plus 1 out. So this is going to be just integrating this like p to n, which is p to the n plus 1 over n plus 1. Evaluate at 0 and 1/2. You're going to multiply it by n plus 1. Subtract all of that from 1. The n plus 1s will cancel out, and this will end up giving you 1 minus 1/2 n plus 1 minus 0. So it's just going to end up being this 1 minus 1/2 to the n plus 1. Yeah, and yeah, that's it for this problem. So it's just like a beta pattern matching problem. Key things to know is that you should know how to like posterior update. It's like pretty chill. You could derive it again, but it would take a long time. Just know that uniforms are beta 1, 1. You add the number of successes to the first one and number of failures to the second one, then you get the posterior distribution. Also, just like keep reminding yourself that p is like a random variable. That will help a lot. And I guess for this first one, it's maybe easier to know beta, to know Bayes billiards. But if you don't, then just knowing how to beta pattern match in a pinch is good. Yeah, so that's problem 7. And I'll see you guys in the last problem, which is problem 8. Good luck studying.